To test if the molecule is basically chiral or not chiral in the lab, what we do is we use a small instrument which we call polarimeter, and that instrument allows the polarized light to travel through a sample tube that has your organic compound in it. And if your compound is chiral, this means that it has a mirror image. Then the plane of polarized light will be rotated by an angle which we call alpha. And if your compound is not chiral, this means that it doesn't have a mirror image, your plane of polarized light will exit without any rotation. So plane of polarized light is basically is the light that has an electric vector. It oscillates in a single plane. So this is basically the ordinary light. And when it passes through a polarizer, the polarizer is one of the components of the polarimeter. It becomes a plain polarized light, and it consists of only those beams that vibrate in the same plane. It's those plane of polarized lights are the ones that basically are going to pass or travel through the sample tube and be rotated by a certain angle if your compound is chiral. And if your compound is not chiral, they're just going to exit the sample tube without any rotation. So we're going to give the term optical activity here an explanation, which is basically a definition here for the molecule being able to rotate the plane of polarized light. So when I say that the molecule is optically active, I mean by that it's basically a chiral molecule that has a mirror image. So a chiral molecule that has a mirror image is an optically active molecule. Optically active means that the molecule is capable of rotating the plane of polarized light. How would you know? You have to do the actual experiment. Put your sample in the sample tube in a polarimeter, and then shine a plane of polarized light on it and see if your plane of polarized light will be rotated by an angle which is alpha. If it is, then your molecule is called optically active. This means that the molecule has a mirror image and it exists as a pair of enantiomers. Now, just know that enantiomers, they do have identical chemical and physical properties. The only difference between enantiomers is the rotation of the plane of polarized light. This is the only difference between the enantiomers and there, because one pair of enantiomer rotates the plane of polarized light into one direction, and the other enantiomer rotates the plane of polarized light in another direction. So if I look closely into a polarimeter, it's made up of a light source. That light source over here, the light source shines light in all directions. This is the ordinary light. It passes it through a polarizer, and then we're going to end up having a beam exiting in here. This is the plane of polarized light. That plane of polarized light is going to enter your sample tube. And if your sample is if your sample is not chiral or achiral, this means that it doesn't have a mirror image, then the plane of polarized light is going to exit the sample tube without being changed. Then we say that the molecule is optically inactive, meaning that it's incapable of rotating the plane of polarized light. So the term optically active or optically inactive is precisely for, or is reserved for, just rotating the plane of polarized light. Remember that compounds that are chiral, meaning that they have mirror images, they are optically active. They are capable of rotating the plane of polarized light by an angle alpha. So here we have a compound in the sample tube that is optically active. This means that it has a mirror image. So it's capable of rotating the plane of polarized light by an angle alpha, which you can easily read from the exit slit of the instrument. That is going to be the angle alpha. And what you're going to be basically measuring is the observed rotation. This is what you measure. You measure the observed rotation. There is a relationship between the specific rotation, which is a standardized physical constant for the amount that a chiral compound rotates the plane of polarized light, and it depends on the length of the sample tube. Normally, the length of the sample tube is always in decimeter, and also it depends on the concentration of your sample. Of course, with the polarimeter, what we are measuring is the rotation of the plane of polarized light in your sample. So all your samples has to be aqueous. They has to be aqueous in there. So we normally prep a dilute solution, and we put it in the sample tube, and then we shine the light on it, and we check the rotation of the plane of polarized light in there. This is an example given hexagrams of sample was dissolved in that much volume of solvent. So you need to make a solution, and then you need to put it in the sample cell. And you do have the length of the sample cell is 5 centimeters. So you have to change this into a decimeter. It's telling me alpha, that the observed rotation alpha in sodium line is that much degrees. You would need to calculate the specific rotation. I already have the observed rotation, I have the length, and I have the concentration. I have all of those. By the way, the concentration is 1.5 grams here in 10 mils. Change it to 1 mils. So divide by basically 10. So that is going to be 0.15 grams per mils. Put everything together and you can get the specific rotation. So the plane of polarized light is rotated by enantiomers. So basically one enantiomer, these two are mirror images of each other, okay? So these two are mirror images of each other over here. So if I have a sample of these molecules there, one of them is going to rotate the plane of polarized light to the right, and the other one is going to rotate the plane of polarized light to the left. Rotating the plane of polarized light to the right, we're going to call it clockwise. Rotating the plane of polarized light to the left, we're going to call it anti-clockwise. So if the rotation is clockwise, we say that the compound is dextrorotatory, and normally we label it by a small d or a positive sign, and we include it in the naming. Now, there is no way for you, because this is an experiment, there is no way for you to know the sign if it is a plus or minus without me giving that to you. So if I give you a plus sign in front of the name, just know that the molecule here is a chiral molecule. It has a mirror image, and that plus sign corresponds to the enantiomer that rotates the plane of polarized light to the right. The negative sign is basically when the plane of polarized light is rotated counterclockwise. So the basically the negative sign here is a representation of the plane of polarized light that is rotated counterclockwise or anti-clockwise, and that is called levorotatory. It's a small l or a negative sign in there. So it corresponds to that enantiomer, and that enantiomer, I would know that it rotates the plane of polarized light to the left. So this one rotates the plane of polarized light to the right. This one rotates the plane of polarized light to the left. Notice, the plane of polarized light is rotated to the same extent, but opposite signs. So one enantiomer will rotate the plane of polarized light in one direction, and the other enantiomer will rotate the plane of polarized light in the opposite direction. So this is going to be your specific rotation in this case. When we represent a specific rotation, normally we represent it as as a form of temperature. So the 21 here is the temperature, and the D is the type of light that we are using. Here I'm using sodium light, it's a deuterium light. And D stands for deuterium in here and there. So this is the type of light that I am using. I'm not done with this one. Okay, so the positive and the negative signs, those represent optical rotation. And this optical rotation, you can only know it in the lab when you do the experiment. These two are called relative configurations. So the positive and the negative, we call those relative configurations. And it's specifically for rotation of the plane of polarized light. There's another type of configuration, and that configuration is the most used one. And that configuration is basically around the chiral center. It's that configuration that you basically can do on paper. And we call this the absolute configuration. It's the configuration or the rotation around the chiral center. So chiral centers can either be rotated clockwise or counterclockwise. If they are rotated clockwise, then we call this an R, absolute configuration, and we have to include it in the name. If the chiral centers are rotated counterclockwise, then we call this an S, and this also has to be included in the name. Now, how can we determine the absolute configuration of the molecule? Normally, there are rules, and we're going to start by first locating our enantiomers, and then locating the chiral center. So let's say, for example, if you have a chiral center in here, this is your chiral center, and let's start with this simple example. We have 4 different groups around this chiral center. So you're going to assign each group bonded to the chiral center in here in order of decreasing atomic number. So you're going to start with the highest atomic number to the lowest atomic number. So the bromine has a higher atomic number than a chlorine, than basically a fluorine, than a hydrogen. So you assign them from the highest atomic number to the lowest atomic number, like this: 1, 2, 3, and 4. Again, in here, what I am doing is I'm checking the rotation around the chiral center. And the rotation around the chiral center can be either clockwise or counterclockwise. In order to check the absolute configuration around the chiral center, I have to set the priorities of the groups around the chiral center. And to set the priorities of the groups around the chiral center, I have to go with the highest atomic number first. So I arrange my groups around the chiral center from the highest to the lowest atomic number. The lowest atomic number is always group number 4. That is a very important one. Now, the second rule is if 2 of the atoms on the stereogenic centers are the same. So let's say, for example, here, if I am looking at this chiral center, okay, this chiral center, it does have 4 different groups around it. It has a hydrogen, it has a CH3, it has an OH, and it has an ethyl group. All of them are different, so this is going to be a chiral center in there. So this is my first step. Locate your chiral center. Now I need to arrange the groups in the order of decreasing atomic number from the highest to the lowest. However, you never, ever, ever consider the group as a whole. Like, for example, if I am looking at the chiral center, the first thing I need to look at is what this chiral center is connected to, and I go 1 atom at a time. So I cannot say that this carbon chiral center is connected to an OH. It is not. It is connected to an oxygen. So you go 1 atom at a time. So the carbon is connected to the oxygen. It's connected to a carbon on this side, a carbon on the other side, and a hydrogen. Now, if 2 atoms are the same on the stereogenic center, like here, I have a carbon here and I have a carbon there. These 2 are the same. Now you have to look at the next atom. So here the carbon is connected to a hydrogen. Here the carbon is connected to a carbon carbon is connected to a carbon. Here, the carbon is connected to a hydrogen. Notice I didn't say this carbon is connected to a hydrogen. No, because I have a carbon, carbon. I have a chain. So the carbon is connected to a carbon, carbon is connected to a hydrogen. Definitely this one is going to be a higher priority, higher atomic number. So see how am I going? I'm going one atom at a time. I cannot consider the ethyl group as a whole. This is not right. So now this is going to be 2. This is going to be priority 2. So this is going to be priority 1 because the oxygen, between the oxygen, 2 carbons and hydrogen, this is the highest atomic number. Priority number 2 is a carbon-carbon versus a carbon-hydrogen. So this is a priority 2. Priority 3 is a carbon-hydrogen versus a hydrogen. So this is a 3. I'm left with the hydrogen being the lowest priority. It's going to be group number 4. This is how you assign your groups around the chiral center based on their atomic number. If 2 isotopes are bonded to the stereogenic center, always arrange in the order of a decreasing mass number from the highest mass to the lowest mass. So let's say if I have the isotopes of hydrogen, the tritium, the deuterium, and the hydrogen in there, then I need to arrange those in the order of decreasing mass number. Tritium has the highest mass number compared to hydrogen having the lowest mass number. Remember, isotopes, they have the same atomic number, but different mass numbers. Okay, so they have different neutrons in that case. Rule number 4. Now, let's say, for example, to assign a priority to an atom that is part of a multiple bond. So if you have a carbon double bond carbon, a carbon double bond oxygen, what are you gonna do in this case? There's a rule that says that a carbon that is connected to a double bond oxygen means that the carbon is connected to 2 oxygens and the oxygen is connected to 2 carbons. See? So the carbon here is connected to 2 oxygens and the oxygen is connected to 2 carbons. So when you set your priority, instead of writing it like this, a carbon double bond carbon, you simply write it like that, so that when you go one atom at a time, you can easily figure out your atomic number and your priorities in this case. A carbon double bond carbon is a carbon that is connected to 2 carbons. So this carbon is connected to 2 red carbons, and the red carbon is connected to 2 green carbons. So in reality, a carbon double bond carbon is a structure that looks like this. A carbon triple bond carbon is a carbon that is connected to 3 red carbons here, and that red carbon is connected to 3 green carbons on the other side. So a carbon triple bond carbon is equivalent to this structure in here. It's drawn like this. That will help you a lot whenever you are setting your priorities. So let's assign the priorities to the stereogenic center in this case. So here's your stereogenic center, you guys. 4 different groups. This is the skeletal form, and these are the same, but I'm showing the structural just to make it easy on you. So assigning the chiral center, I do have 1 chiral center in there. So let's assign the priorities. I have a bromine. So this is priority 1. So that's the highest atomic number because between a bromine, let me highlight this. So between a bromine, see how did I go? I went with a bromine, carbon, chlorine, hydrogen. I didn't go with a CH2I, because if I went with CH2I, that whole thing is going to have a higher atomic number than the bromine. So I didn't go with that. I went with 1 atom at a time. So you start with the atoms that are connected to your chiral center first and set your priorities according to the atomic number. Now, if you have a tie, move on to the next atom. So here I don't have a tie, so I don't even have to go to the iodine. I know I have a bromine. This is atomic number. This is the highest atomic number. And then I have a chlorine. This is the second. So this is 1, 2. And then I have a carbon. This is a third. And then I have a hydrogen. This is a fourth. These are my priorities. This is a chiral center over here. So let's go there. This is your chiral center here. So that chiral center is connected to a carbon. See, a carbon. See, the first thing I go with, one atom at a time. If I have a tie, so notice, all of those are carbons. Now I need to look at the adjacent atom. So this carbon is a branch. It's connected to a carbon because it's a CH3 twice. So it's connected, it's this. It's a CH that is connected to a CH3 and a CH3. So it's as if I am viewing a carbon. See, carbon. This is it. So I have a carbon. This is a branch. So this is going to be priority 1. Connect or compared to a carbon. So now here I'm having a tie. These two carbons are a tie with these two carbons. Go to the third carbon. This is a CH3. This is a CH2. Okay, now this CH2 is connected to a carbon. This CH3 is connected to a hydrogen. So this is going to be your second priority. This is going to be your third. This is going to be your fourth. Again, I didn't go with the whole pentyl group. I didn't go with that whole group. I went one carbon at a time. And once I hit a tie, I look at the adjacent atom. Once I hit a tie, I look at the adjacent atom. I keep doing this until I find a difference. And then I set my priorities based on that. Now, if you have an OH and a carboxylic acid, this is a carboxylic acid. This is a carbon. This is a carbon. Here you go. It's a carbon double bond OH. What did we say over here? We said that okay, so if I am looking at the chiral center in there, that chiral center is connected to a hydrogen, it's connected to an OH, and it's connected to, see that carbon with a double bond O? It's as if it's a carbon with two oxygens and an oxygen with two carbons, okay? So this is the carbon double bond O, and then on that carbon I have an OH. So basically, let me highlight this. See, all of that is the double bond O. See how I divided it so that I made it easy. I made it easy to view. Okay, and then on that carbon, I have a carbon in there. And then, of course, I'm having my two hydrogens there. And then I'm having my OH. Now, if I want to set my priority, this is going to be my chiral center because I have 4 different groups. Now I need to look at the connectivity. I have an oxygen here. Okay, let's use another color. I'm having an oxygen there. This compared to between an oxygen, carbon, hydrogen, oxygen is the highest priority. So this is why this guy over here is going to be priority number 1. And then now, see, I'm having a tie between carbon, COH, it's a tie, coming, COCH, then definitely this is going to be 3. This is going to be 2, This is going to be 2 over here. This is my carboxylic acid group, this is going to be 2. And then this guy over here is going to be compared to the hydrogen, this is going to be 3. Then my lowest priority is always a hydrogen, and it is going to be 4. Now, once you go ahead and set your priorities, you now need to determine the rotation around that chiral center. And that rotation, we named it as absolute configuration, okay? And the configuration is going to be either clockwise or counterclockwise, either R or S. You are doing a rotation around a chiral center in this case. So you hold your molecular, and this is where the molecular models come in handy. But I will show you a trick and let you watch a small video. If you don't have your molecular model with you, what are you going to do? So, so you set your priorities in there, and then see how am I looking? You look directly at your chiral center. Once you set your priorities, the way that you have to look in a way so that your lowest priority is behind. You don't want to see it. So build your tetrahedral molecular model and make sure that your lowest priority group is basically behind. You cannot see it. So look across your chiral center, and then behind your chiral center, you're going to see carbon number or group number 4 there. Group number 4 you shouldn't be able to view. It has to be behind. So when it is behind, what now you're going to see only are groups 1, 2, and 3. And you basically go around based on their priority. So I am going over here as groups 1, 2, and 3. I'm going with my rotation like this. See how am I going with my rotation? I'm going with my rotation clockwise. So going with my rotation clockwise, this is going to be my R configuration. So the rotation around the chiral center, this chiral center is going to be R. The way that I did it, I looked away from group number 4. The lowest priority group has always to be behind. You can easily visualize this once you build your molecular model. Arrange your molecular model in a way so that your lowest priority group is basically away. You cannot see it. And then go with the configurations from the highest atomic number to the lowest atomic number and figure out the rotation around the chiral center. So this is going to be enantiomer A. Enantiomer A here has a rotation clockwise. Clockwise means an R. If enantiomer A has a rotation, one rotation, then around the chiral center with a certain direction, then enantiomer B will have a rotation in the opposite direction. So the enantiomer B here, I'm expecting it to be counterclockwise. The way that I do it, exactly the same. You look at the chiral center. So you look at the chiral center and they're away from group number 4. Group number 4 has to be behind. And then once you locate group number 4 behind, then go ahead, set your priorities in there. So I have group number 1, 2, and 3. So now I'm going this way from 1, 2, and 3. And that is going to be counterclockwise. Normally enantiomers, one of them is going to have a certain configuration. The other one's going to have another or an opposite configuration around the chiral center. So here, the two enantiomers are going to be, one is going to be an R isomer and the other one's going to be an S isomer. And this is what differs enantiomers from each other. They have the same name, but the rotation around the chiral center is different. So you have to include the rotation around the chiral center in the name. So when you're naming it, you have to locate where is your chiral center. Here in this case, my chiral center is on carbon number 2. This is 1, this is 2. This is naming of alcohols. We didn't discuss this yet. But to name alcohols, you simply give the OH the lowest number. So this is why I started numbering from the side. And you need to locate where your OH is. So your OH is on the second carbon. So that is going to be 2. It's a carbon chain of 4. So it's a butane. You drop the E and put an OL. OL is an indication that you have an alcohol in there. This is the name, 2-butanol. But since you have a chiral center, you have to check what is the rotation around that chiral center. What's the configuration? Is it an R or is it an S? So you have basically to include that in the naming. So around that chiral center, I have basically a clockwise rotation, so or configuration. So this is why on carbon number 2 that is going to be an R. This is carbon, this is 1, 2, carbon 2 is going to be an S configuration. So that is going to be the S isomer in this case. Now let's say, for example, if your lowest priority group is not facing behind, what do you need to do? So always we said that the lowest priority group has to be behind. if your lowest priority group is not behind, so here in this case, carbon number 2 or group number 2 is behind, what do I need to do? All what you need to do is just do a rotation. Rotate. This is what you need to do over here. So I do have a, okay, click here. Okay, here you go. So this is in one of your problems basically. Okay, this is in one of your problems in here. Assume that this gray ball here is the hydrogen. Okay, so here I do have a hydrogen. I do have a chlorine. Let's do the labels in there. So I have an oxygen, nitrogen, chlorine, and assume this one is the hydrogen, okay, just to show you. So we said that group number 4 has always to be behind. So let's say, for example, if a group number 4 is in front, it's like this, it's in front. What do I need to do? So all what you need to do, basically, hold your molecular models, in case you have a molecular model with you, hold your molecular model and simply rotate so that group number 4, let's do the rotation, see, group number 4 now is at the back, I cannot see it. So now I have 1, 2, and 3, 1, 2, and 3, and then you do your configuration. This is your molecular model. So again, if you have your molecular model with you, hold your molecular model and look away from your group number 4. Make sure that your group number 4 is always behind. If your group number 4 is in front, then all what you need to do is just do a simple rotation and make it at the back. And once you make it at the back, then look basically away from it and do the configuration. So look in this direction and here, away from it, you shouldn't see it at all, and then do the configuration, and it's going to be 1, 2, and 3, and that is going to be clockwise. In this case, it's going to be an R configuration. This is in case you have a basically your molecular model with you. Simply, as simple as that, you do the rotation. Make sure that group C, group number 4 here, this is not in front. Group number, this is not behind, I'm sorry, this group number 4 is in plane. So all what you need to do is just do a simple rotation and make sure that the group number 4 is behind, and then go ahead and do your configuration. In that case, you're going by 1, 2, 3, this is the S enantiomer. Here, going by 1, 2, 3, this is the R enantiomer. Notice when I figure out the R and the S enantiomers, my lowest priority group is always behind, and I'm looking across 1, 2, and 3 away from group number 4. You have to really understand one thing here, that from one carbon and 4 different groups around it, you can get 2 possibilities that are mirror images of each other. There's a video in here. This is the YouTube channel. This is the video that I really want you to watch. In case you don't have a molecular model with you, this really comes in handy. It's a small trick that you can do in order to figure out the configuration without having a molecular model with you. So simply, since we said that if you have 1 carbon in 4 different groups, you're going to end up with 2 possibilities that are mirror images of each other. You cannot have more than that. So you're going to end up having a pair of enantiomers from the carbon in 4 different groups. You're going to end up having a pair of enantiomers, which basically 2 possibilities that are mirror images of each other. So now, by swapping any 2 groups, so if I'm swapping here any 2 groups, you change normally the configuration of the molecule. See, if I, let's see how I'm going to do this. So if by swapping here, let's select that. Okay, here you go. So that is the eraser. Okay, so, okay. So let's say, for example, this is my tetrahedral carbon, 4 different groups. I'm setting my priorities. Here in this case, group number 4 is in plane. It is not behind. What should I do? I don't have a molecular model with me. So all what you need to do over here is simply swap a group 4. So I'm just going to go ahead and take a group 4 and the group 2. I'm going to swap them. See, now group 4 is behind. By swapping any two groups, normally you change the configuration of the molecule. And the configuration that you're going to get is that of the mirror image of the molecule. So here by swapping, I made carbon number 4 behind. So now I'm just going to look from here. I'm going to look from here away from carbon 4 and set my priorities. And my priority is going to be 1, 2, and 3 like that. This is going to be basically an S configuration. Now that S configuration is for the enantiomer. It is for the mirror image of the molecule. So I'm just going to go ahead and cross it. And because I did the swapping, so I'm going to go ahead and cross it. And now my new configuration is going to be the opposite. So it's going to be an R. So my configuration for the molecule is basically going to be an R. So by swapping any two groups, you change the configuration of the molecule. Here I made carbon number 4 behind. It was in a plane, I made it behind because I cannot do the configuration if the lowest priority is not behind. So when you swap, you get basically the configuration of the mirror image. So here I swapped, I got the configuration of the mirror image. So to find the configuration of the molecule itself, you have basically to reverse that, to change it, and I'm going to change it into an R. Whenever you have enantiomers, so if you have enantiomers in there A and B, one of them is going to be a certain configuration, and the other one is going to be the opposite configuration. One of them is going to have a rotation counterclockwise. The other one is going to have a rotation clockwise. So if I got the configuration for the mirror image to be an S, then definitely the configuration of the second enantiomer has to be an R. So this is going to be the configuration of my molecule there. This is how you do it if you don't have a molecular model with you. If you had a molecular model with you, all what you need to do is just do the rotation so that carbon number 4 is behind, and then go 1, 2, 3. You're going to get the same configuration there, which is the R configuration. So let's have an example. Draw the structure of S1 bromo 1 chlorobutane. This is 1 bromo 1 chlorobutane. Let's go ahead and draw the structure of that. Normally what I would do is I would put the longest carbon chain in a plane. It's always the case. The longest carbon chain, put it in a plane and there. If you have the chance to put the hydrogen behind, put the hydrogen behind because this is your lowest priority group. This is a group number 4. And then you have a bromine and a chlorine. It's up to you to put either one of them in front or in plane. But since I want an S configuration, I want my highest priority group to be on this side now, so that I can go 1, 2, 3 as a counterclockwise S. If the bromine is up there, then my priority is going to be, this is going to be 1, this is going to be 2, there's going to be 1, 2, 3, it's going to be an R. So pay attention to that. So this is why bromine has to be in front here. Set your priorities between a carbon, a chlorine, a bromine, hydrogen. Bromine is priority 1, chlorine is priority 2, carbon is priority 3, and hydrogen is priority 4. Then basically look away from 4. So I am looking here, okay, away from 4. And when looking away from 4, I'm going from 1, 2, okay, this way. So I'm going counterclockwise. So I'm going to end up having my S isomer. So the configuration around this chiral center is going to be the S configuration. Draw the structure of 2R, 3R. Now, this means that I have 2 chiral centers. When I have one configuration, it means that I have one chiral center. And notice here, because the chiral center is on carbon number 1 in the structure, so this is carbon 1 in the structure, I did not have I did not have to label it as one S over there. So, so whenever you have two configurations, then this means that you have two chiral centers in there. Each one has an absolute configuration, has an absolute rotation, okay, around the chiral center. It's the rotation of the groups around the chiral center there. So I want to draw 2R, 3R. The first thing, as I said, make your long carbon chain in plane, and then all what you have to do here is basically work with the groups hydrogen and the chlorine. Okay, now since you need an R configuration, now I always prefer to put the lowest priority group behind. I always prefer that lowest priority group behind. So going by 1, this is going to be priority 1. This is a carbon chlorine. This is a carbon hydrogen. So this is going to be priority 2 on this side, and then priority 3 on that side. And hydrogen is behind, looking this way. So hydrogen is going to be behind. I shouldn't see it. I'm going by 1, 2, and 3. This is clockwise. It is an R configuration. For this chiral center, I have priority 1, which is the chlorine. I have the second priority here. Why the second priority here? Because I'm going with carbon chlorine versus carbon carbon. So that is going to be my second priority. It's going to be my third. Hydrogen is behind. I shouldn't look at it. So basically what I'm viewing it is from the top. Hydrogen is going to be behind. I shouldn't see it. So I'm going by 1, 2, and 3 like that. It's going to be 1, 2, and 3. And this is going to be clockwise. Is the molecule R or S in here? Now, this is the trick. This is the trick over here. Hydrogen is the lowest priority group, is not behind. So either do it with the molecular model or do it with the swapping. But if you swap, you get the configuration of the mirror image. So you have basically to change your configuration. So so here let's set the priorities. We have this is my chiral center. I have my CO, so this is priority 1. This is a C2Os, this is a priority 2, and then this is a priority 3, and that is going to be a priority 4 in this case. Arrange them like this, so 1, 2, 3, 4. Okay, so this is basically my priority in here. Now, the thing is, my CH3 is behind. I want my hydrogen to be behind. So all what you need to do is just swap the CH3 with the hydrogen, just to swap them. Okay, so let's go ahead and swap those. So I'm just going to take the CH3. I'm going to take the CH3 and see that hydrogen. I'm going to take this hydrogen here. Okay, it's going to let me. Here you go. So this is the hydrogen. This is the CH3, just to swap those. And now I have my lowest priority group behind. I'm gonna look through this axis here so that not to see the hydrogen, so through this side. And then I have, this is gonna be priority 1, priority 2, priority 3. So I'm going by 1, 2, 3 like that. 1, 2, 3 like this, away from the hydrogen. And that is going to be basically my R configuration. Now the R configuration is for the enantiomer because I swapped it. When you swap it, you change it to the enantiomer. So you got your configuration for the enantiomer. If you want the configuration for the actual molecule, you need to cross that and reverse it. So my configuration for the actual molecule is going to be an S. You can get this result either by the swapping method, if you don't have your molecular model in handy, or if you had your molecular model, it's so easy. You simply locate one axis and rotate around that axis so that this hydrogen is behind. And when the hydrogen is behind, you go 1, 2, and 3, and that is going to be counterclockwise. This is an S configuration. Label the stereogenic centers in the ball and stick model. following, okay, this is a drug that is used to treat high pressure. So it's a large drug over there. So let's see how many chiral centers we have. A chiral center is a center that has four different groups around it. So basically I have this as a chiral center, four different groups, 1, 2, 3, 4. I have this as a chiral center, I have this as a chiral center in there. So basically I have three chiral centers with four different groups around them. Now for the configuration, again, group number 4 has to be behind. See, it is behind. I can simply do the configuration in here. That blue ball stands for nitrogen. So that blue ball in there stands for nitrogen. Let's have a green color there. Oh, you know what? Let's have a black one. So that stands for nitrogen. So you have a nitrogen in here. So you set your priorities. The red one stands for oxygen. The red one stands for oxygen in there. So that chiral center is connected to a carbon, nitrogen. So this is going to be your higher priority. This is priority 1. On this side over here, this is going to be priority number 2. And then a carbon, this is a priority 3. So I am going by 1, 2, 3 like this. Hydrogen is behind. So the configuration is going to be an S configuration. For this chiral center, I have a nitrogen, so that is going to be, so I have a nitrogen in here, that is going to be priority number 1 for this chiral center. And then I'm having priority number 2, priority number 3 because it's carbon-carbon versus carbon-oxygen. And then hydrogen is priority 4. See, hydrogen is behind, so I'm going again by 1, 2, and 3. And that is going to be counterclockwise. It's an S configuration. When you're doing the configuration, priority number 4 has to be behind. If it is not behind, I have to rotate to make it behind. You rotate if you have your molecular model. If you don't have your molecular models, please swap so that you make it behind. And then whatever configuration you get, that will be for you the enantiomer. Reverse that, and that will be the configuration for your molecule. And then for this one, see how hydrogen is behind there? So I'm going to look from the top. This is going to be priority 1. Okay, so this is going to be priority number 1 because it's a nitrogen. Priority 2 because it's a carbon-oxygen, 2 oxygens there. And then priority 3 because it's a carbon-carbon. Hydrogen is behind. And I'm going 1, 2, 3 again like this. This is counterclockwise, so it's an S configuration.